Electropermanent magnet relay. A relay of conventional design develops a pull-in force for any polarity of the current. By adding a permanent magnet to the structure, a polarized relay is obtained. It can develop both the pulling and pushing forces. Relay consists of a coil winding placed inside the ferromagnetic core and a movable anchor that incorporates steel parts and a permanent magnet. Permanent magnet coercive force is 500 kA per meter. Winding number of turns is 600 and the rated current value is 1 ampere. Our task is to calculate force acting on the anchor at rated current in the winding and the force at zero current. The relay geometry features rotational symmetry and we can simulate it in two-dimensional axisymmetric model. Okay, let's start QuickField now. In QuickField I create new problem. Problem name permanent magnet relay. Next. Problem type is magnetostatics. Model class is axisymmetric, length units are millimeters. Finish. On the left you can see the problem pane and on the right you can see the geometry model editor window. You can draw the geometry model here or you can import the geometry model from the AutoCAD DXF file. Here I have the geometry model already prepared and I will import it. Here is the geometry model imported. You can see the cross-section of the relay. In axisymmetric problems, the axis of the rotation is a horizontal one and we should draw only the upper half of the cross-section. Here you can recognize the coil, the core and a moving part. Let's assign labels. Through labels we will provide material properties. Switch to Select Objects mode, click to select the block and assign label Core. Select Conductor and assign label Winding. This is a permanent magnet and these parts are steel. Hold the control button pressed to select multiple objects at the same time. In fact, the magnetic field is distributed not only in steel parts, but also in the air outside. QuickField cannot simulate magnetic field distribution in the infinitely large space, so we need to restrict the simulation domain. Zoom out, switch to Insert mode and draw the air block boundary. First a horizontal line, then change the line type to be the half arc and draw the half arc. Now switch to Select Objects mode, click the air block and assign the label Air. Now let's provide physical properties for labels. Double click the label name in the tree. Relative magnetic permeability of the air is 1. Okay. Relative magnetic permeability of the winding is 1. It is made of copper. And the total current value is 600 turns multiplied by 1 total ampere turns. Okay. For the steel parts the relative magnetic permeability is non-linear, and here in the Excel file I have the BH curve data. Just select this data, copy, paste, close. Okay. And the core is made of the same steel. Okay. Permanent magnet relative magnetic permeability is 1.05. The coercive force magnitude is 500 kiloamperes per meter, and the direction is to the left, which is 180 degrees. Okay, that is all for block labels, but we should also assign labels to the boundaries. QuickField automatically assigns proper boundary condition on the axis of the rotation, and I will use default condition on the external boundary. So the geometry model and the data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button, save all problem files, and run the analysis. The problem has been solved, and we can take a look at the results now. Here you can see the magnetic field lines, and you can adjust the field picture. For example, I will switch on the color map of the flux density. Okay. The correspondence between colors and the numbers you can see in the legend. To get exact value of field parameters, you can use the local values tool. Click any point and get the flux density, field strength, and other parameters. And you can edit the coordinates here. You can also use contour tool and construct XY plot. For example, here I click these edges on, switch on the XY plot. This is the flux density in the permanent magnet, and on the left and on the right are the flux density distribution in the steel parts. And the numbers you can see in the table. Coordinates, flux density, magnetic field strength. Of course, you can draw any arbitrary contour. Just change the line type, click and drag, then release. You can also use contours to calculate integral values. Contour clear. I will select these blocks by clicking inside blocks. Open the integrals, mechanical force. This is the force acting on the anchor, and you can see that the force is pointing to the right. The anchor is pushed out of the relay solenoid. So we have come to the next task, calculation of the mechanical force at zero current. That's easy. I just need to change the data in the winding. Change the current from 1 to 0 amperes. Okay, solve the problem, save all modified files, open the results, use the contour tool to select the anchor elements, follow to the integrals, and the mechanical force now is 2.3, pointing to the left. The anchor is pulled inside the solenoid. If you search for the Electropermanent magnet relay on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. The simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.